Welcome back everyone. In this lecture, I am going to demonstrate how one can use involution functions to prove some very strong statements. So, what we are going to do is I am going to show you an ingenious proof of Don Zaiger's. He proved that P congruent to 1 modulo 4 type of primes can be written as sum of two squares using only involution maps. So, let me state the theorem and then we will slowly actually prove this, and of course, this theorem can be proved using some more advanced algebraic ideas that you will be seeing in the later part of the course that involves understanding the quotients of this polynomial ring that is defined over integers. But anyway, so this proof uses only some elementary number theory, so which I will take it as a block box. So, I am not going to prove, and then so we will write down explicitly the involution map that is involved, and we will check that map is involution, and then using that involution map we will actually prove like how one can write given prime which is of the form P congruent to 1 modulo 4 as sum of two squares. Okay, so that is the theorem. So, every prime P congruent to 1 modulo 4, so can be written as P equal to A square plus B square for some A and B natural numbers. Okay. So, we are going to prove this nice theorem using only combinatorics or involution maps. For that, let us try to first understand what one can do with involution maps. Suppose let us say we have a set S. So, we assume it to be non-empty set, so that we can talk about functions on that, and suppose we have this iota which is a map from S to S. Let us say this is indeed an involution. We already seen that the iota composition iota must be identity on S, that is the definition. So, iota composition iota is identity on S. In particularly, the iota must be an injective map. Okay. So, if we take a finite set, non-empty finite set, so then any injective map from S to S will be bijective. So, this is a fact which I am going to use it, and it will be proved when we discuss about cardinality of a function, cardinality of a set. So, the very first fact which I am again hiding under the carpet is that any injective map from S to S must be bijective, okay, since S is assumed to be non-empty finite set. So, now if I have actually a set S with this map iota, so then what I can do, I can talk about fixed points of this map. So, we say an x in S a fixed point of this map iota if the iota of x is equal to x. Okay. So, now what we can do, we can actually partition this capital S into actually the orbits of this like map. Okay. So, again this is something we will again discuss in detail when I talk about partitions, but here this case is very clear. So, let us actually talk about it. So, let us say S is given to be some x1 etcetera xk. So, now what I can do, I can actually look at this iota applied on x1. Okay. So, x1 is there and then iota of x1 is there. Now, the thing is either x1 is equal to iota of x1 or not. So, if it is equal, what I can do, I can just take x1 only, I am not going to worry about its image. If it is not equal, I just pair it with that image. Okay. If this is equal, then take singleton 1, singleton x1. If x1 is different from iota of x1, take x1 comma iota of x1. Okay. And this procedure I do it for all elements. So, that means what I can do, I can partition this S as this x comma iota of x as a set, where we get disjoint union of this, where x will come from some indexing set lambda. Okay. So, I am going to just pair x with its image. Now, you collect this set x comma iota of x. Either this x iota of x becomes singleton, in that case x equal to iota of x, or it is going to be 2 set. Okay. So, S will be written as these collections of what is called orbits. So, now it is clear that the number of elements in this S becomes equal to, you just collect all possible this sum. So, that means this is going to be equal to summation 1, where you collect this I such that xi equal to iota of xi, and then plus summation 2, where I such that xi is different from iota of xi. So, this is something we are getting. So, this means the cardinality of S is going to be the number of fixed points modulo 2, that is for sure. So, this is what we get immediately using this equation. So, you collect those I, those xi, okay. Basically this I is coming from 1 to k. So, this I is coming from 1 to k, such that xi is being equal to its image iota of xi, and then xi not being equal to iota of xi. So, you collect them. So, then S is just union of them. So, disjoint union of them. So, in particularly the number of elements in S will be equal to these two sums. So, that means the cardinality of S is going to be congruent to, okay, the number of fixed points modulo 2. That means the difference between these two numbers is divided by 2. So, 2 divides the cardinality of S minus number of fixed points. Okay. So, this tells us that if you have a fixed point, let us say the number of fixed point is odd, then cardinality of S must be odd. Okay. So, as a corollary we get, if number of fixed point is odd, then that cardinality of S is odd. Okay. So, this is what we are getting. Okay. So, now what we will do, we will construct a set S and an involution, and then use that in order to prove this result. Okay. So, again the motivations of this proof comes from the studying the algebraic proof of this theorem and then formulating it in terms of the combinatorics. So, I can't get into that. So, I am going to just write down the set and we will prove that set is non-empty, and then we will define an involution on that and then prove that is an involution, and use that to conclude something about given prime P is being sum of squares. Okay. So, what is the set? So, take set S to be the tuples x, y, z, where they are coming from natural numbers. Okay. X, y, z's are positive integers. So, positive integers for me 1, 2, 3 etc., such that x square plus 4 y z is given by P. Okay. So, this is the set that we are taking. So, now if you think about it, okay, so here let me just put this aside. Okay. If you can take an element something like this in this set, x like y, if it is in S, okay, then that would imply immediately that x square plus 4 y square is equal to P. That means, I can take A to be x, B to be 2 y, then P becomes A square plus B square. Okay. So, that means we need to look for some element that is of this form. But how do I get something like that? So, if you think about it, I can look at this involution f from S to S, okay, where I just take this x, y, z and then send it to x, z, y. Okay. I just switch the last two coordinates. Note that this 4 times y z appears in this sum, then switching this y z is not going to change the definition of this tuple. Okay. So, that means there is this natural involution which actually takes x y z to x z y. Okay. So, now if you think about it, okay, we need to prove this S is non-empty. So, that is indeed an result from actually yeah, it is a result from number theory. So, and this S is being finite, that is very clear. Okay. So, that is the block box I was telling. So, that this is non-empty. Okay. So, S is being non-empty. So, this is that I am going to take it as a fact. Okay. I am not going to prove. Now, why S is finite? Because x square is less than or equal to P, that would imply that x is at most square root of P. And similarly, you can see that y, z both are at most P. So, this implies x, y, z all of them are bounded above by P. Okay. So, that implies that S is finite. Okay. So, this means S is a finite set. So, now what we need to prove? We need to prove that F has a fixed point. Okay. If we prove F has a fixed point, then that would imply that let us say x, y, z is a fixed point of F, then F of x, y, z is going to be x, y, z. But we know what is f of x, y, z, which is x, z, y, and this would imply that y equal to z. And if you see, that is what we wanted. So, we wanted a tuple x, y, 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 that is in capital S. So, that would immediately tell you that I can write P equal to A square plus B square. Okay. So, now how I am going to do this? To do this, what Don Zaiger did, actually he came up with another involution, which is very nice involution, and using that involution he actually proves that the cardinality of S must be odd. Okay. The claim is that the cardinality of S is odd. So, now if you go back to our observation, the cardinality of S is congruent to the number of fixed points of any involution iota modulo 2. So, this tells you that if cardinality of S is odd, then this is exactly 1 congruent to the number of fixed points of any involution iota, okay, where iota is any involution. So, this is something we observed for any involution. So, this tells that immediately if cardinality f is odd, then the number of fixed points of iota must be not equal to 0, because if it is 0, then this equation cannot happen. So, that would tell you that f has a fixed point, that will complete the proof. Okay. So, the core part of the proof is that we need to say cardinality of S is odd. Okay. So, it actually immediately implies the fact that S is non-empty as well. Okay. That is also something like you can get it for free, because odd numbers cannot be 0. Okay. So, this is the ultimate goal. So, to prove this cardinality of S is being odd, so Don Zaiger he actually wrote down this explicit map. So, let us actually write it down. So, I am going to call this map alpha from S to S. So, which is given by, so this map alpha x comma y comma az, which is defined based on the cases. So, let us try to understand the cases that actually appears. Okay. So, if you go back to the equation that we have x square plus 4 y z equal to p. So, x square plus 4 y z is p, that is what we have. So, now first thing to realize is that y minus z is going to be strictly less than 2 y, since x, y, z all of them are greater than or equal to 1. That would tell you that y minus z is less than or equal to y minus 1, which is less than or equal to, like we can put strict inequality. So, yeah, if y is, this is going to be strictly less than 2 y, because y is greater than or equal to 1. So, that means y minus z is always less than 2 y. Now, given x, what would happen? Okay, given x, then we will have 3 possibilities. So, let us plot this y minus z. So, y minus z is somewhere here and 2 y is somewhere here. So, given x, either x can lie here or x can lie here or x can lie here. Okay. So, these are all the 3 possibilities, and we can easily see x will never be equal to the boundary values. Okay. So, let us try to see. Suppose x equal to y minus z, then we have this equation x square plus 4 y z is p, then that would tell you that y minus z square plus 4 y z, which is equal to p, but y minus z square is y square plus z square minus 2 y z plus 4 y z, which gives us exactly y plus z whole square. Since y and z both are greater than or equal to 1 and p is prime, we get a contradiction, because we have written p equal to y plus z whole square, a contradiction. Okay. So, that means x is never equal to y minus z. Okay. Similarly, let us see x is can be 2 y. If x is 2 y, then what happens? So, again we can substitute there 2y square plus 4yz equal to prime p, but then that would imply that I can take 2y outside, it becomes 2y plus 2z. Again we are getting factorization of p. So, that implies 2 divides p, which is contradiction. Okay. So, that implies x is also not equal to 2y. So, that means, so the way we plotted, we can see that y minus z is here, 2y is here, and excluding these two. So, either x lies here or x lies here or x lies here. Okay. Now, depending upon that, we are going to define the function that we wanted to define. So, when x lies between minus infinity to y minus z, so that means x is less than y minus z, then you define this to be x plus 2 z comma z y minus x minus z. Okay. This is the tuple you take. If x lies between y minus z and 2y, then you take 2y minus x comma y comma x minus y plus z, and similarly you take x minus 2y comma x minus y plus z comma y if x is bigger than 2y. So, this is how the map alpha is defined. So, our claim is that this alpha is an involution, okay, and that would indeed complete the proof, because alpha will have we need to prove that alpha will have some fixed point. Okay. So, what are the things that we want to prove? So, let me write it down. So, alpha is an involution. The second is alpha has a unique fixed point, and from this we conclude the cardinality of S is congruent to mod 2. That implies the cardinality of S is odd. Okay. So, these two only we need to really check. The last one follows from our earlier discussion. Okay. So, let us first check this 2, that it has indeed only one fixed point. Okay. So, let us look at the case 1 where x is less than y minus z. So, recall alpha of x y z is defined to be x plus 2 z comma z comma y minus x minus z, and suppose this is a fixed point, then this is going to be equal to x comma y comma z. So, that means we have the following equation x equal to x plus 2 z, and this would immediately tell you that z is 0. So, that means we have z is 0 and y is z, that would imply that y is 0, and now you can see the last one is that z equal to y minus x minus z, that would imply if z 0 y 0 then x is 0. So, this gives us contradiction, because we have that x square plus 4 y z is exactly equal to prime p. If all of them are 0, then p becomes 0, which is not correct. So, that means there is no fixed point. So, this discussion says there is no fixed point in this setting x less than y minus z. Okay. So, this is done. So, now let us take the case 2, which is like x is greater than 2y, and then look at what happens. Recall the way we defined alpha of x y z, which is exactly given by x minus 2y comma x minus y plus z comma y. So, now if it is equal to x y z, then this equation will tell you alpha of x y z equal to x minus 2y comma x minus y plus z comma y, and this would imply immediately that x equal to x minus 2y, then that would imply y is 0 and y 0 will imply z is 0 by looking at these two coordinates. And if x and y z y and z are 0, then already we have x square equal to p, which is a contradiction because p cannot be a square. That means there is no fixed point if x is greater than 2y. So, that case is also done. Now, look at what happens case 3 when x is lying in between y minus z and 2y. So, in that case alpha of x y z is exactly given by 2y minus x comma y comma x minus y plus z. Okay, this is we want it to be x y z. So, that tells you that x equal to 2 y minus x, that would imply y equal to x. Now, y equal to y. So, the second equation is okay, and the third equation z is equal to x minus plus z. Okay. So, now if x equal to y, then that would imply that z equal to z. So, this is equation also. So, that only solution that we have is this x y z should be equal to x x z, but we know that x square plus 4 y z is supposed to be p. So, then if you substitute x equal to y in this, then you get x square plus 4 x z equal to p, but this is nothing but x into x plus 4 z is equal to p. Since both x z are greater than or equal to 1, this should force x equal to 1. So, there is no other option. If x equal to 1, that would imply p equal to 1 plus 4 z. Now, note that such a z exists because we assumed p is congruent to 1 modulo 4, and that means there exists k such that p equal to 1 plus 4 k. Okay. So, you can take z to be that k. So, that means I have this solution x equal to 1, y equal to 1 and z equal to k, and k is unique. Okay. There is no two different k we can get because k is defined using this equation p equal to 1 plus k. That means we have this fixed point which is 1 comma 1 comma k, and it is unique fixed point, unique fixed point. Okay. So, that means that we could conclude if we prove that that alpha is an involution, alpha is involution would immediately imply the cardinality of S is congruent to the number of fixed points of alpha modulo 2, but the number of fixed points we just proved it is exactly this one fixed point. So, that would tell that the cardinality of S is congruent to 1 modulo 2, that would imply the cardinality of S is odd. Okay. And this indeed completes the proof of the main theorem modulo that we check this is indeed an involution. Okay. So, if you think about it, it actually like you can directly check, it is not a very difficult thing to do. So, let me just write down what is supposed to be checked and then you can check properly. call this capital A, which is a subset of S, which is you collect all those triples x, y, z in S such that x is satisfying the first equation, okay, sorry, first inequality, x is less than y minus z. You call it B, again the tuple x, y, z in S such that it satisfies the second inequality, y minus z is less than x less than 2y. Then the C, you call it as x minus 2y, sorry, x, y, z in S such that x is greater than 2y. Okay. The exercise is that alpha of A is contained in C and alpha of C contained in A and alpha of B contained in B. Okay. And alpha, composition alpha is nothing but identity on S. Okay. One can directly check this. Maybe I will check one of them and then leave remaining thing to you to check. Okay. So, let us check that alpha of A is subset of C. So, start with x, y, z in A, that means x is less than y minus z. Now, alpha of x, y, z is defined to be x plus 2y z y minus x minus z. So, now call them as x dash, sorry, x1, y1 and z1. What we need to check? We need to check that this alpha of x, y, alpha of x comma y comma z belongs to C, but C is defined to be x is greater than 2y. So, that means we need to check x1 is greater than twice y1. Okay, that is what we need to check. But what is x1? So, x1 is nothing but x plus 2y, y1 is z. So, that means this is exactly 2z, and we need to check x is greater than x plus 2y is greater than 2z, which is obvious because x is already given to be. So, x is to begin with less than y minus z. So, minus x is greater than z minus y, but x is positive. So, x is greater than minus x. So, this implies this is exactly twice z minus y. Okay. So, this tells that x1 is greater than 2 y1. Now, we need to check again alpha of x y again is an element of S, not only checking this inequality, it is an element of S, that is something we need to check. That means x1 square plus 4 y1 z1 should be equal to again prime p. So, this is the most important thing. So, in particularly if you we do this computation directly and then see x plus 2y square plus 4 times z times y minus x minus z. This is what we need to compute. We will just compute it directly. This is x square plus 4y square plus 4xy plus 4yz minus 4xz minus 4z square. Okay. So, I guess I have made some mistake. Yeah, so it is supposed to be z here. So the very first term is x plus 2 z comma y minus x minus z. So then if you go back to these calculations, so let us write it properly. So x1 is x plus 2z, and if we want it to be inside C, then x1 should be greater than twice y1, which is 2z, which is true because x plus 2z is greater than 2z. So, this is true. So, only thing we need to check is this alpha of x y z is again element of capital S. So, which again like x1 is 2z. So, you replace here 2z square, and then here it becomes 4z. So, now you can see the cancellation, this can cancelled with this and this get cancelled with this. So, what you get is exactly x square plus 4y, which is we know already p. That means alpha of x y z is in S again. So, that verifies that alpha is a map from A to S. So, now what happens to alpha of alpha x y z? So, let us compute this. This is going to be alpha of this x1, which is x plus 2z z y minus x minus z. But note that this is going to be inside your C. So, when it is inside your C, then the definition of alpha of, let us say this is x1, this is y1 and this is z1. Alpha of x1, y1, z1 is nothing but x1 minus 2y1 comma x1 minus y1 plus z1 comma y1. So, this is the definition. So, let us look at it closely and then compute what is x1 minus 2y1, which is exactly equal to x plus 2z minus 2z, which is x. So, what you got here is x comma. So, y1 is clear, y1 is exactly equal to z. So, you get z here. So, what is the second coordinate? Second coordinate is x1 minus y1 plus z1, which is exactly equal to x plus 2z plus y minus x minus z minus z. So, this z get cancelled and x get cancelled, you get y. Okay. So, that tells alpha square of x y z is exactly x y z. Okay. So, this tells you that at least on capital A, alpha restricted to A maps A to C and alpha square is identity. Again, the remaining things can be checked similarly, that alpha of C map to A and alpha of B map to B, and alpha square is again identity. So, that proves that alpha must be an involution. Now, once it is an involution, then the number of fixed points will be congruent to cardinality of S. Since the number of fixed points is 1, that would imply that the cardinality of S is indeed odd. Okay. And that implies that in particularly S is non-empty, okay, which is also we need to prove in order to prove the important fact. So, that means we have this cardinality of S is odd, and if you go back to the involution, natural involution that we consider, x y z goes to x z y, that will have fixed point and that will give you the required A B that we wanted. Okay. So, this set that we constructed comes from out of the blue, and then like first thing to notice is that it is non-empty, even that requires proof, and once you prove that, then you are like you need to prove the cardinality of that is odd, okay, that you prove using the techniques that we have it from the involutions and looking at its fixed points. Okay, so yeah, this is what I wanted to actually tell you about some application of this involution, and yeah, with this I will stop here. And in next class what we will do, we will start with axiom of choice and partitions of sets and so on. Okay, I will stop here. Thanks.